now we're going to look at a different way to represent sequences, which is with something called recursion. So this says function explicit formulas are convenient because you can plug in the number of the term or the n value to find the term. There is another way to define the terms in a sequence. So imagine you're in 4th grade. You know about addition and multiplication, but you have no idea what a function is. If you saw the following list of numbers, how would you describe it? Make sure you give enough detail so it is the only list of numbers that can be generated with your description. So if I asked this of a 4th grader, probably they'd look at the numbers and they could figure out that they have to add 5. But part of what you want to do is make sure that it's the only list of numbers that can be generated. Okay. Now, if I said make a pattern that adds 5, I could do this pattern, right? So that's not the same pattern, but it fits the rule that I currently have there. So what we also need to define this sequence in a way that it's the only sequence we could make is we have to say start with 6. So if I said start with 6 and add 5, maybe we'll add a little more to get the next term, we can continually add 5 and we could create that sequence. So looking at the next one, we're going to do the same thing. So I would pause the video and just kind of quickly write down what 2 pieces of information similar to this would you need to know to completely define this list of numbers in that way. Great, so looking at this list, we're going to do that start, right? We have to say what we start with. So start with 60. Okay, and looking at this actually has a dividing pattern, which we want to express as a multiplying pattern to kind of to go with that geometric series. So we could say divide by 2, but I'm going to write multiply by 1/2 to get the next. So basically what you've just done is made something called a recursive definition. To make a recursive definition, you say the term you start with and what you had to do to get to the next term and the next term and so on. So in some ways, recursive definitions are more natural. Like anyone can kind of come up with that and not really have to know a lot about math or notation or anything like that. So why are recursive definitions so hard for people? Basically, as soon as we throw in notation, they start to get kind of like hard to look at and hard to think about. So that's why I always kind of start with this, like, baby steps. A 4th grader could do this, right? And then we'll throw in the notation and it won't be so bad. So the most important thing to do, if a sub n is the term you're trying to find, how would we represent the term before it? So let's say I'm trying to find a sub 5. The term before it is a sub 4, okay? So therefore, the term before it, if this is an n, the number before n is n minus 1. So we're going to see this a sub n minus 1 in our recursive definitions. So to make a recursive definition with notation, it basically looks like this. And the 2 things you need is you say, where does the sequence start? So we say a sub 1 equals 6. So that's the same thing as saying this, start with 6. And then to get a term, I take the last term and add 5. So that's like if I want a sub n, I need to take a sub n minus 1 and add 5. If I want a sub 5, I have to take a sub 4 and add 5. So we're going to use this definition. Now, once you get recursion, you can kind of just look at it and write it out. It's actually, in some ways, as I said, there's positives of it over the explicit definitions. But here, we're going to actually use the notation. So we already know a sub 1 is 6. And we want the next 4 terms of the sequence. So one thing about recursion is I have to find the terms in order, because I need to use the one before it to find the next one. So if I want to find a sub 2, I take the term before it, a sub 1, and I add 5. So a sub 1 is 6, right? So I'm going to do 6 plus 5 is 11. So the next one we have to find is a sub 3. So if I want to find a sub 3, I take the one before it, which is a sub 2, and I add 5. So the one before it, a sub 2, is 11. So I'm plugging that in. I do 11. Hello. 11 plus 5. And that gives me 16. So continuing on, a sub 4 equals a sub 3, right? The term before it plus 5. A sub 3 is 16, so 16 plus 5 is 21. And then it wants me to get the next 4 terms, so I have to also find a sub 5, which is a sub 4 plus 5, which is 21 plus 5, which is 26. Okay. Now, as you get used to this, you do not need to write that much, okay? But that's the idea of what's going on, so you kind of get like all the things that once you start doing stuff in your head, that's what's happening. Okay, so let's look at the next one. It says, here we have a formula, a sub 1 equals 30. And to get to the next term, I do 1/2 times the last term. That's basically, or the term before it. That's what this is saying, that a sub n and a sub n minus 1, this is subscripts, this is the number of the term down here, and this is the one that came before it. So to get a sub 2, we do 1/2 times a sub 1, and that's a big thing. Like, if you're going to get confused, you need to know the subscript numbers are not a number that you calculate with. They're telling you what term to look at, okay? So they don't get multiplied by anything or like thrown into the problem. A sub 1 is a thing or a value, and that value is 30. So that's 15. So if you're ready for it, you can think about it. I'm doing 1/2 times the last term. The last term was 15, so I can just do 1/2 times 15 is 7.5. And to get the next one, I do 1/2 times a sub n minus 1 would now be a sub 3. So that's 3.75. Okay, they just wanted these 3 terms, and we have them. So I could always take the terms. I know we wrote some work out. So this list looks like 30, 15, 7.5, 3.75. Okay, dot, 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 because it would continue on if we found more. So those were the same 2 problems that we defined up top, where we just looked at the lists, but so it's just, kind of to make it simpler to get all this notation stuff down, and then we'll start to look at some other sequences. So here is the section. I'm not going to write it in words. I'm going to talk about it in words, okay? So when I see this sequence, I know it's recursion because I see the a sub 1 equals, and I also see some of this where there's like multiple spots with subscripts, and I see the a sub n and a sub n minus 1. So in words, we're starting with 3, and to get the next term, I do 2 times the last term, and I add 1. Okay, so that's what's happening in words. So I'm going to do this once, but I know some people aren't ready for this. So I'm starting with a 3. To get the next one, I do 2 times the last one. So 2 times 3 plus 1, that's 6 plus 1 is 7. To get the next one, I do 2 times 7 plus 1. 2 times 7 is 14 plus 1 is 15. To get the next one, I do 2 times 15 plus 1, which is 31. Okay, it says next 4, so we have one more. 2 times 31 plus 1 is 63. Okay, so that's when you really get recursion. You can look at it, you just figure them out because it's a pattern. Times 2 plus 1, times 2 plus 1, times 2 plus 1 is basically that pattern, okay? If we're going to calculate it, I would actually write out to get the second term, okay, do 2. If this is a 2, that's a 1 times the first term plus 1. So that's 2. A sub 1 is 3 plus 1 is 7. So that's the full workout. I'm going to do that one more time. To get the third term, I take the second term times 2 plus 1. So 2 times 7 plus 1 is 15. Skipping this step, we now know we just have to take that last one, which was 15. Okay, and to get the fifth term, 2 times 31 plus 1, which is 63. So wherever you're at, I mean, and this is one of those things that like is tricky for some people. So if you need to, ask your teacher, even if you watch the videos, do that, okay? But that's the basic idea. Once you get it, you can kind of just write them down. Okay, so these are gonna throw in a couple of other little things. I'm actually not gonna worry too much about the function notation one. On this video, I'm gonna do B and C, okay? So on this one, what's different now is this, okay? I don't know why anyone writes it this way, but sometimes they do. So just so you've seen it, basically the n plus 1 is 1 bigger than the a sub n. So I actually just cross this out and I switch them over to the way I like to see it. Except I crossed over, so now I don't know what it says. So minus 10. So having a plus 1 and a nothing is the same thing as having just a sub n and n minus 1. It's just 1 bigger. Okay, so this notation means the same thing as that. I know normally we can't just like change stuff in math, but we're just referring to their relationship to each other, that this is 1 bigger than that. So it's the same thing as n and n minus 1. So if I said this in words, start with 4. To get the next term, take the last term, square it, and subtract 10. Okay? So I'm starting with a 4. To get the next term, I square the last term, so 4 squared minus 10. 16 minus 10 is 6. Okay? So now 6 squared minus 10 is 26. And from here, I'm going to turn to my answer key because the numbers are going to get too big for me. So the next one, 26 squared minus 10 is 666. Okay. And then 666 squared minus 10 is 443,546. I'm not going to put a comma there because then I feel like it'll look confusing and it'll look like it's 2 separate terms. So if I was using the formula, to get the second term, which I have to find after that first term, I take the first term, which is a 4, square it minus 10. 16 minus 10 is 6. Then I take the last one squared minus 10. 36 minus 10 is 26. Take the last one squared minus 10, and that's 666. Take the last one squared minus 10, and that is 443,546. Okay, so letter C is a little trickier because they also have an n value here. So this one I find harder to do in my head because I have to keep track of a couple different things. So I'm actually just going to talk about this one. We'll say the words, and then I'm actually going to just write this one out, not go straight to writing it out. So part of math is being flexible, saying like, oh, I could do this one in my head, but this one I need to write stuff down. Okay, so, and talk to your teacher about whether or not they want to see this type of work all the time. Okay, but basically, when you look at this one, I suggest writing it down. So here, I'm going to start with 5. To get the next term, I take the last term and add it to whatever value of n is right here. So keeping track of that with that type of like list we were doing just in our heads is kind of tricky, especially if this expression with n gets more complicated. So I'm going to find a sub 2 next. So to find a sub 2, I'm going to write this one out. Take a sub 1, right, the term before it, and add the value of n. Now this is not a subscript, this is a regular number 2, okay, because n is a regular size here, okay? So a sub 1 is 5, 5 plus 2 is 7. So to get the third term, take the second term and add the value of n, which is now 3. So that is 7 plus 3 is 10. Take the third term, the last term, to get a sub 4 and add the value of n is 4. So this is 10 plus 4 is 14. A sub 4 is 14. 14 plus 5 is 19. So my numbers are 7, 10, 14, 19 for those next 4 terms. So just a comment about this function notation one. Basically, I would probably also rewrite this one in subscript notation. So this is f of n and f of n minus 1, so that's the same thing as that. Okay, so we've changed it to subscripts, and then this would just be a sub 1 equals 4. So it's just a different notation, not something to get scared of. So I'm not going to do this one, but in words, to get the next term, I do 2 times the last term minus the value of n squared.